Howdy gang, welcome back. I appreciate you being patient with me. I had to wrap up cooking a little bit here. But today is an interesting day. We're in a bit of a limbo spot right now because you guys are ahead of my other Calc 1 class. So I want to spend some time today sort of tying up odds and ends and just solving some problems. I'm also going to, as promised, show you a little bit the connection between Katie's lecture on antiderivatives yesterday and the material that we'll be talking about moving forwards. So I'd like to begin today with any homework questions you guys want to look at. Turn on my screen share, log back into this. So go ahead in the chat, let me know if there are any homework problems you've been looking at, banging your head against the wall on, just getting frustrated by anything like that, where we'd like a little nudge. You would like to see number 19 from homework 10. Okay, and go ahead and do the same. Anybody who has a problem they would like to see, I would be happy to help with that. Number 19, this is fun. This hinges on that theorem that we ended with on Monday. No, this is the theorem that I showed before Katie's lecture on Wednesday. That's when we talked about this. So they say if little m is less than f of x is less than big M everywhere between a and b, where little m is the absolute min, big M is the absolute max, then this inequality is true for the integral. We want to estimate the integral using that theorem. So I'll kind of redraw that picture. But let's do it for this particular function. All right. So the function they've given me to integrate is x cubed. And we want to integrate from 0 to 4. They say, I'll couch this slightly differently. Find lower and upper estimates for the integral from 0 to 4 of x cubed dx using the theorem little m times b minus a is less than or equal to integral a to b f of x dx less than or equal to big M times b minus a, where for little m we use the absolute min of f of x on a b, and big M we use the max of f of x on so this is the goal. The problem here, this is homework 10 number. Remember where this inequality comes from, right? It was the 3-color shaded picture from the start of class on Wednesday. I have that picture here. All right, so you remember this guy? This is really what we're saying. So the pencil shaded area, remember, is the integral from a to b. The purple shaded area is little m times b minus a, and the blue shaded area, this area, is big M times b minus a. And big M could be any upper bound for f, and little m could be any lower bound for f, and this inequality would still stay true. But in order to get the inequality as tight as possible, we want big M to be the least upper bound for f, aka the absolute max. And we want little m to be the greatest lower bound for f of x, aka the absolute min. So this is what we're using. So I think it is healthy to draw the picture. And if f of x is x cubed, and we're looking from 0 to 4, there's 4 right here, x cubed, of course, goes through 0. When x is equal to 4, 4 cubed is 64, so I will label that up there as 64. We have a horizontal tangent here. We are growing quite quickly by this time. So something like this. This is the graph of x cubed. And of course, it goes on over there like that. The exact area, which is what the integral would be measuring, is again shaded in pencil. Consistency, so right, so this is the area that the integral is going to calculate. The values I'll use for little m and big M. Little m is the absolute min of f of x equals x cubed on the interval 0 to 4. And we don't need to do anything fancy to find this because we've got the picture right here, right? So this is why the picture is so nice. What is the absolute min of x cubed, this curve? This is x cubed. What's the absolute min of this function on the interval 0 to 4? 0, right? It's right here. This is the smallest that function ever gets on the closed bounded interval from 0 to 4. So this is going to be 0. And capital N is the absolute max of f of x equals x cubed on 0 to 4. You could use the closed interval method to do this, but again, the picture makes life so much easier. What is the absolute max of x cubed on the closed interval from 0 to 4? So let's be careful there. It occurs at x equals 4, but what is the max value? Remember we said, what is the min, what is the max? Those are y values. Yeah, good, 64. All right, and then we can add those into the picture. Little m down here is going to be a little hard to see. 0. And big M up here is 64. So then sort of my blue shaded box is all of this, which is clearly a massive overestimate. And my purple shaded box, you can't even see it's down here because it's 0. And of course, that's a massive underestimate. But what this tells me is that little m, which is 0 times b minus a, which is 4 minus 0, is less than or equal to the integral from 0 to 4 of x cubed dx, is less than or equal to big M, which is 64 times b minus a, which is 4 minus 0. So what we're saying is that the gray area is between the purple area and the blue area. And the purple area is 0, right? 0 times 4 is 0. And the larger area here is 4 times 64, that's 256. So these would be my upper and lower estimates. This integral is somewhere between 0 and 256. It's a real rough estimate, all right? That's like saying I live somewhere between here and Miami. It's not very helpful. But it is nevertheless true, and this is what the theorem gives us. We could get better estimates here by using Riemann sums. But this is what the problem asked us to do. So is this satisfactory? Are there any questions we'd like to explore deeper here?
Is it B to A or 0 to A on the bottom part?
So this is B minus A, and this is B minus A. So we're integrating from A to B. And the idea is that the width of that interval is always the right endpoint minus the left endpoint. So when I'm calculating the length of this interval, which is the width of both of the rectangles, that's always B minus A. Yeah, I imagine that what WebAssign is going to do here is the thing that works more generally, which is use the closed interval method to find the absolute min and absolute max. And in a more complicated problem, that is the thing to do. But for this particular guy, finding the absolute max and absolute min is really trivial. Because we're not finding the absolute max for the function everywhere. We're finding the absolute max of the function on the interval 0 to 4. So we're restricting our attention just to this interval. And the absolute max is right here. And the absolute min is right here. So it's true that if I don't restrict to a closed bounded interval, then this function has no max. It would also have no min, because it would go off to negative infinity over here. But if we restrict any continuous function to a closed bounded interval, we always do get a particular min and a particular max. All right. I think there was at least one other question that showed up here in the chat. Let me take a look at that. Number 15. Let's look at 15. Here it is. Oh, yeah, this is cool. All right. So we want to find the integral from 0 to 6 of f of x, where f of x is this piecewise defined function. Oh, sorry, give me just 1 second. All right. So we want to find the integral from 0 to 6. Let me get this out of the way. Where f of x is a piecewise defined function. Did I just close that? Oh no. Okay, yeah. 4 and x. We're equal to 4 if x is less than 4. And we're equal to x if x is greater than or equal to 4. So I know that graphing piecewise functions is one of those things that not every pre-calc class does in the depth it should. So the first thing we need to do here is definitely to draw the graph. The trick to drawing the graph of any piecewise function is to just know the graph of the pieces. So the function y equals 4 is a constant function. Here's my x-axis. The function y equals x is a linear function with slope 1 and y-intercept 0. And then the game to get the graph of this from the graphs of these is to just hold on to the parts specified in the piecewise business. So this guy says, I behave like x equals 4 or y equals 4, this. if x is less than positive 4. So let me just, I'll call this 4. And that means I'm going to take, oh, I should have made that an open circle. All right. I'm going to take just this part. Because that's the part of this graph where x is less than 4. And similarly over here, if I call this 4, it says I behave like y equals x, but only if x is greater than or equal to 4. That means I'm going to take just this part. So if I want to draw the graph of f of x, here's what that will look like. I'm going to mark this as 4, and I'll mark this y value here as 4. Everywhere to the left of x equals 4, I behave like the constant function y equals 4. And everywhere greater than or equal to 4, I behave the y value here, this point is 4, 4, because we're on the graph y equals x. So it happens to be the case that this point gets filled in by the second piece, and then it behaves just like y equals x from there. So this is the graph of that piecewise function. This right here is the graph of this piecewise function. And what they want is the integral from 0 to 6, which is the exact area bounded by that function from x equals 0, which is over here, all the way up to x equals 6 over here. So we're looking for this area. That's the idea. Now this one is pretty convenient. I can calculate all of this area using geometry. I would split it into a few different regions. Probably I would split it like, okay, here's a big rectangle. And here's a little triangle. So the rectangle area is equal to this base times this height. The base here is length 6 times the height is 4, so that's 24. And the little triangle area is 1/2 times this base times this height. The base here from 4 to 6, that's 2 units. And the height here we need to think about. So this point earlier I identified as 4, 4. What is the point up here? Well, it's f of 6. Right, this is on the graph of f of x. And f of 6 is 6. So the base here is 2, and the height here is also 2. Yeah, excellent. Okay. So then the area of the little triangle is just 2, right? 1/2 times 4. And the area of the rectangle is 24, 6 times 4. Therefore, the integral from 0 to 6 of f of x dx is equal to the exact total area, which is 24 plus 2, which is 26. So that's what we're looking for here. There are other ways to do this. There are other ways to split this region up into pieces you can find the area of. There are ways to attack this integral directly, but I think this is by far the simplest way to solve this problem. Questions on this guy? Alrighty then. Last time we saw a handful of good antiderivative problems. I think it would be healthy to summarize kind of all the antiderivative stuff we should know. So to that end, I'm going to give you a collection of antiderivatives you must know. I'm going to do this in the little f, capital F notation. So first, a constant. If I want to find an antiderivative for a constant, who differentiates that constant? Well, just c times x. This is actually a special case of the power rule, which Katie proved for us last time. An antiderivative for x to the n is 1 over n plus 1 times x to the n plus 1. And this works great for all n except -1. In the case where n is -1, what you're really looking at there is 1 over x. This is the same as x to the -1. And this guy would have as his antiderivative the natural log of the absolute value of x. And we talked a little bit, Katie showed us where this absolute value is coming from. If you differentiate the natural log of -x, you get 1 over x. And if you differentiate the natural log of positive x, you get 1 over x. So the most general form of that is to just say that in general, 1 over x has antiderivative natural log of the absolute value of x. This works everywhere that this function is defined. And it happens to be the same place this function is defined. E to the x is antiderivative is e to the x, of course. Hamlet. No, be good. You got a toy? Oh, I'm sorry. The toy is okay. You can play with the toy. That's all. I'm sorry. Don't know. If we have another base exponential like b to the x, his antiderivative would be 1 over the natural log of b times b to the x. And this comes from the fact that if you differentiate b to the x, you get b to the x times the natural log of b. So to anti-differentiate, you get b to the x, but you have to get rid of that natural log of b that would come from the derivative. That's why we divide by it. There are some important antiderivatives coming from trigonometry. An antiderivative for cosine x is sine x. An antiderivative for sine x is negative cos x, because the derivative of cos is negative sine, and negative sine is sine. Tangent and secant do have antiderivatives, but we're going to need some more sophisticated tools to find them. But some other trig stuff that we can find antiderivatives for are like secant squared of x. we know that the derivative of tangent is secant squared. So the antiderivative of secant squared should just be tangent x. And kind of next to this, cosecant squared has antiderivative negative cotangent x, because the derivative of cotangent is negative cosecant squared. So the derivative of negative cotangent is positive cosecant squared. Same sort of logic as the cosine thing here. Secant x tangent x has antiderivative secant x. And so cosecant x cotangent x has antiderivative negative cosecant x. And you'll notice some patterns here between a given function and its co-function. They follow the same sort of thing, it's just that the co-function has a negative. The last few that I'll ask you to know, right? These are the ones that I'm going to test you on, being clear. There's more of these, of course. The textbook has a few tables of these. These are the ones I'm going to test you on. 1 over 1 plus x squared, we saw in Katie's example the other day, has antiderivative arctan x, or inverse tangent of x. And then finally, 1 over the square root of 1 minus x squared has antiderivative inverse sine of x. So these are the basics. These are sort of the building blocks. And really, it's just derivatives backwards, right? That's all an antiderivative is. So every differentiation rule or formula that you've remembered, you can read it backwards to get an anti-differentiation rule or formula. Especially these guys down at the bottom here. These guys are all just things that we're used to knowing, but in the other direction. The derivative of these is these. But of course, that means that the antiderivative of these is these. And these guys up here kind of feel new, and they kind of are new. So this is sort of the new stuff, and this is just reading old stuff backwards, but you need to know it all. Let's see, we did plenty of IVPs yesterday. We did plenty of that other stuff. So I don't feel compelled to spend extra time on those if you guys don't have specific questions from the homework, which means we are kind of ready to start talking about FTC. I think maybe the way to do this is going to be to play with it a little bit. So I don't want to give you the fundamental theorem of calculus outright and then just prove it and say, okay, now this is something you need to know. I would like for you to come along with me and sort of discover it. To that end, we're going to look at a kind of interesting problem. Let's examine the function capital F of x equals the integral from 0 up to x of, let's say, 2t dt. So I'm doing a few things here. I'm introducing some notation that will be fairly common down the road. The evocative use of a capital letter here should remind you of an antiderivative. And I think we'll be able to sort of discover the fundamental theorem of calculus as a consequence if we're able to really understand this thing. So recall that the integral from 0 to x of 2t dt, this is equal to the area under f of t equals 2t from t equals 0 to t equals x. Right? That's all that this guy means. That's the nicest way to interpret it. You could write it as a Riemann sum if you wanted, but that's pretty intimidating. So instead of playing with Riemann sums, let's look at some graphs. Here's my graph f of t equals 2t. I'll call this 1, 2, 3, 4. So then capital F of 0 is the area from 0 to 0 under 2t dt. Well, how much area is there under this curve from 0 to 0? Don't think too hard about this. Yeah, there ain't shit there. What about capital F of 1? Well, that would be the integral from 0 to 1 of 2t dt. That is this area. Right? Which is 1/2 base times height. This is a little triangle, yeah, because this is a straight line up here. This is going to be a little triangle. So this is 1/2 the base times the height. Well, what's the height? What's the point on this graph? Since this is, yeah, go ahead.
Yeah, it's 2.
Yeah. So this is 1, 2. So the height there is 2. The base there is 1. So this is 1/2 times base times height, which is 1/2 times 2, which is just 1. If we look at capital F of 2, this would be the integral from 0 to 2 of 2t dt, which is the area under my curve from 0 all the way up to 2 here. Which is this whole shaded area now, right? The big triangle here. And again, thankfully it's a triangle, so we can compute the area as 1/2 base times height. This point is 2, 4. So that area is 1/2 base, which is 2, times the height, which is 4. The 2 and 1/2 cancel, so we just get 4 here. And I'll look at f of 3 and f of 4 as well. F of 3 would be the area of this whole triangular region. And here, the point up here along f of t equals 2t is 3, 6. So my base is 3, my height is 6. This is 1/2 times 3 times 6. 1/2 times 6 is 3, so this is 3 times 3, which is 9. And I think you'll start to see the pattern. 0, 1, 4, 9. Let's calculate f of 4 and then see what we get. Integral 0 to 4 of 2t dt is going to be 1/2 base times height, because again, we're looking at a triangle. This time we're looking at this triangle. And the point up here is 4, 8. So this is 1/2 times 4 times 8, which is 16. So what sort of pattern do we notice? F of 0 is 0. F of 1 is 1. F of 2 is 4. F of 3 is 9. F of 4 is 16. Based on this pattern, it appears to be the case that capital F of x is what? Yeah, x squared. These are all the squares of the inputs we're feeding. Now, I want you to think for a minute. What's the relationship between this guy and the function I'm integrating, 2t?
It's the derivative.
Yeah, if I differentiate this and then plug in t, I get 2t. So this, which satisfies capital F primed of x equals 2x, or otherwise written capital F primed of t is 2t, which is little f of t. So another way to say this is that the integral is an antiderivative. There's a little bit of funkiness going on with the variables. The way we usually say it is like this. We would say this is, rather than saying I can plug t into that, I would say I can plug x into the guy inside. And this is the first part of the fundamental theorem of calculus. There's nothing special about the function 2t here. So this is called FTC1. This hints quite strongly at the first part of the fundamental theorem of calculus. FTC stands for fundamental theorem of calculus. Says that if little f of t is continuous, then the function constructed as the definite integral from anywhere up to x of little f of t dt is differentiable. And capital F primed of x is little f of x. In other words, integrals are antiderivatives. Now there's, again, a little bit of funkiness going on with variables here. And I want you to take the time to get comfy with it. The second part of the fundamental theorem is actually the more useful. And I don't want to give you too much ahead of time, because it really is worth digesting these pieces one at a time. So before I even start to hint at FTC2, I'd like to just show you an example or two using FTC1. So if I define capital F of x to be the integral from -1 up to x of e to the t dt, can we find, I'm going to make it e to the -t, why not? Find capital F primed of x. Now here I don't want to draw the picture, because the area under e to the -t, that's not made up of triangles. This is going to be considerably harder. So instead, I'm going to identify the pieces and interpret this through the lens of FTC1. As in FTC1, little f of t here is e to the -t. So capital F primed of x should just be little f of x. So if I take this little f function and I swap the t's for x's, that should give me capital F primed. So this is like mind-numbingly simple. It's this. Here's another example. If capital F of x is the integral from 1 to x of 1 over t dt, find capital F primed of x. And again, as in FTC1, little f of t here would be 1 over t. So capital F primed of x should be little f of x, which is what?
1 over x.
Very good. Okay, now I want to talk a little bit more about this second example, because we have talked about antiderivatives. So let me do this in a different color. We know that the natural log of the absolute value of x is an antiderivative for 1 over x. Therefore, what is capital F of x here? If capital F primed, that's little f, is 1 over x, then if you want to undo this differentiation and go back to big old capital F, you need to anti-derive this. So what's an antiderivative for 1 over x?
But you already said it.
Antiderivative. So we want to go up the other way on the derivative ladder. Back at that table.
I don't know, after the value left.
Perfect. Yes, exactly. This is going to be the natural log of absolute value x. And this provides a beautiful window not only into the second part of the fundamental theorem of calculus, but also the natural log function, i.e. ln absolute x is equal to the area under 1 over x from x equals, I should say, is equal to the area under 1 over x. I should really say this, equal to the area under 1 over t from t equals 1 to t equals x, right? Because that's what this integral represents. It's the area under 1 over t from 1 to x. So this is, believe it or not, in a slightly more grown-up math class, what's called an advanced calculus class. This is how we define the natural log function. We say that the natural log of a number is the area underneath 1 over x, or underneath 1 over t from 1 up to x. This area is ln of x. And here I'm assuming x is positive, so there's no harm in leaving off the absolute values. Pretty cool stuff, right? This can be used as a definition. Of ln. And it's a much more useful definition than saying it's the inverse of e to the x, because it's a direct geometric representation. So this is just a little bit of extra discussion, because today we've got some time. Okay. Like I said, I don't really want to get too far ahead here. This is hinting pretty strongly at what's called FTC2. That the way to evaluate integrals is to find an antiderivative and plug in the bounds. I'll show you one more problem of this nature maybe, and then we can conclude for the day, because like I said, there's a risk of you getting too far ahead, which would make organization hard. And any questions about these two little examples here involving FTC1? Oh, I know what we can do. I can show you the chain link case. Well, maybe we should save that. We'll save that. So we'll move on to the FTC part of it. Let me see, does the textbook have an easy example here? Because I don't have one in mind. I think they just fucking say it, don't they? It kind of blows. No bueno. Sometimes, Stuart, you really let me down. So are we going to do this right or no? No. To show you. Okay. Let me do this. So this is a low stress moment. I just want you guys to again think along with me. Consider the integral of x dx and assume that a and b are both positive, with b being larger than a. Not a tricky thing to talk about. This is the curve f of x equals x. I'm assuming a is positive and b is larger than a. So the integral there is this area. You know, the point here is a comma a. And the point here is b comma b, because we're along the graph f of x equals x. A handful of ways to calculate this area. You could think of it as this whole triangle minus this little triangle. So let me do it like that. I'm going to say that the shaded area is equal to the area of sort of this big purple triangle minus the area of the little blue triangle. So the integral from a to b of x dx is equal to the area of the big triangle minus the area of the little triangle. What is the area of the big triangle? Well, it's 1/2 the base, which is b, times the height, which is also b. And the area of the little triangle is 1/2 his base, which is a, times his height, which is also a. So what we get here is one half b squared minus 1/2 a squared. Let me actually, I know this might seem a little silly, but I'm going to make the squares black also. So you've noticed that I've colored the 1/2 and the squares black. Just a and b in this final line have the color of the associated space. Anybody see a reason why we might do that? It's a curious choice of color.
To distinguish the triangles.
Specifically, you notice these things have the same sort of algebraic shape, right? 1/2 times something squared minus 1/2 times something else squared. There is an algebra, or there is a notation for this. I would call this 1/2 x squared evaluated from a to b. And what is the relationship between f of x? So now I'd say note. Since f of x is equal to x, this function, since f of x is equal to x, this function, 1/2 x squared, is equal to capital F of x, the antiderivative of little f of x. And just like our last example hinted strongly at one of the fundamental theorems of calculus, this example hints very strongly at what's called FTC2. So if you want to evaluate a definite integral, but you don't want to set up a Riemann sum, what you can do is find an antiderivative for the function that's being integrated and then plug in the bounds. That's pretty wild. And this is where I will leave it today. So you've seen a taste, but we will come with the full force next Monday. And this says, if little f is integrable and capital F is an antiderivative for little f, then the integral from a to b of little f of x dx is equal to capital F of b minus capital F of a, for which we actually, because we use this so much, we develop the special notation, this. And this is the magic, ladies and gentlemen. This is how everybody solves integrals. So for now, this week, you guys aren't using this, right? For now, this week, you guys are working using geometry and Riemann sums because you must. And the problems that I've given you are, for the most part, not problems that you can apply this to, because some people like to try and hack them together using FTC2 instead of actually learning the Riemann sum stuff. Don't do that. But through the remainder of the course after next week and all of Calc 2, this is actually how people solve integrals. You can't imagine, trying to solve every integral in the world by writing it as a limit of a Riemann sum and going through all that bullshit. That's incredibly hard work, and it only works for certain kinds of functions because those summation formulas are incredibly difficult to come up with. All right, we have like 4 of them because those are the only 4 that are easy to derive and share. More generally, if you wanted to integrate something like sine or cosine or tangent, you would never, ever, ever be able to get there using those Riemann sums. But this will work. And it really is coming from this sort of thing. And this sort of thing really is coming from geometry. So next week, we're going to talk a lot about FTCs 1 and 2, the fundamental theorems of calculus. I'll prove FTC 2, and then I'll prove FTC 1 from FTC 2. And you guys will begin to get a feel for what integration is like for most of the world, what it generally means to integrate a function, how we try to do it the majority of the time out there in the broader world. But I hope that having seen a little bit of this sort of simpler characteristic examples helps as we dive into that stuff next week. The only things I need you to do for the remainder of this week is just finish up that homework, and everything that you needed to finish up that homework you really had yesterday from Katie and Monday's lectures. So if you get stuck on anything, come by an office hour. I do have an office hour today from 1 to 2. Otherwise, I will see you guys on Monday. So yeah, this is a good question. I just got a PM asking a couple of things. Will there be a curve on exam 2, and can we replace the lowest grade with the final? Definitely yes to the second one. Absolutely. The final exam will replace your lowest midterm. But having graded your guys' exam 2s, I'm not sure that the same curve I used in my non-honors class is appropriate. Because you guys did much better than my non-honors class, which is what I would expect. But I think I probably will still apply a curve. I just need to talk to my department chair and see what she thinks is appropriate here, because honestly, I've never curved a test before. And in my other class, it was pretty obvious what and where needed to be curved, but this class is a little different for a few reasons. A greater proportion of you took the makeup test, which was different. And you guys uniformly did better than my other class. So I'm trying to decide exactly what to do there, but again, I still have not decided. I did say I would give you a definite decision on that today, right? So here's what I'll clear it with my boss later today. I'm going to move for a 5-point curve, I think, on your guys' tests. Like I said, I've never done this before, and I never intend to do it again. So I'm really against curving exams. The exam in my non-honors class was dreadful, dreadful, dreadful. And I understand there are some weird circumstances going on right now. I don't want to be unfair. So I think probably a 5-point curve is what I'll ask Katie if she thinks that's appropriate. And if she gives me the yes, then we'll go ahead and do that, and I'll apply the curve later today. I've got a department meeting with her at 2, so that'll be a convenient time to ask, and then you'll see the results showing up in Canvas a little later after that, probably around 4 or 5. Any other burning questions before we skedaddle? All right, yeah, so in answer to that last question, yes, the final will replace your lowest midterm. And yes, I will be curving your guys' test as well, but I think just by 5 points, as long as I can get permission from the department. All right, if there are not other questions, I'm going to go ahead and end the session here. Last call. Okay, guys, I hope you have a wonderful rest of your day. Enjoy your weekend. Take a look at the comments I left on your exam too. Curve or no curve, there are things that need improving. You guys were not anywhere near as bad as my other class, but there are still plenty of places there where we need to look at things and be more careful. So please take a look at that stuff. If you do want to talk about anything, you can come see me in office hours or send me a Canvas message. Otherwise, I'll see you guys on Monday. Take care.